So some intro and definitions. Okay, I guess everyone here already knows this, but a partition lambda of some natural number n, we just say is some non-increasing list of integers, lambda 1 to lambda s, such that their sum is n. So for us, there will always be s parts. Okay, what do we do with this? So for this talk, we want to look at the Ferrer's diagram of lambda. So how do you build this? I'm sure everyone's seen, you just place lambda j dots in the jth row. And the conjugate of lambda is formed, you just switch the rows and columns of this diagram. So we'll see an example in a minute. So the partition 3, 2, 1 of 6 just has this Ferrer's diagram. So 3 in the first row, 2 in the second, 1 in the last. Okay, so what's the point? What do we do with these? So for us, we want to look at hook lengths and t-cores. Okay, so if we label the cell of our Ferrer's diagram like a matrix, so I have the top left is 1, 1. Okay, and then we denote by lambda k prime the number of dots in the column k. Then the hook length of the cell jk in the Ferrer's diagram is just given by this formula. And okay, this looks a bit messy, but this is very natural when we come to look at it. If no hook length in any cell of a partition, so if I calculate this formula for every cell in our partition, and if none of these is divisible by t, then lambda is called a t-core partition. Okay, so a brief example. So let's look at the same partition. So the hook length here of the top left-hand cell is just 5. And this weird formula literally just counts this hook here. And if I want the second cell, so 1, 2, this one here, then I look at the hook here. So it just has length 3, so we just count the number of dots in this hook. Okay, if you go through this process for this partition, we have hook lengths of 5, 3, 1, 3, 1, and 1. So what does that mean? That means that this partition lambda is a t-core partition for all t that don't divide these numbers. So for any t not in 1, 3, and 5, this is a t-core partition. Even better for us is that switching rows and columns here leaves lambda the same. So lambda is a self-conjugate partition. In particular, this is an example of a self-conjugate 7-core of the number 6. Okay, why do we care about these things? So there are two major applications that I've come across. So t-core partitions, they capture the representation theory of these symmetric groups Sn and An. And how do they do that? So each partition corresponds naturally to some representation that takes Sn to your GLD over some finite field. And even better than that is that we know that this representation row is irreducible if and only if our lambda is a p-core. And this p is down here on your FP. And this d is just some number. I think it looks like n factorial divided by the product of your hook lengths. So these are intricately related to representation theory of your symmetric groups. The second application is the Ramanujan congruences. So I guess everyone here knows these. So these are the congruences on partitions. And they've been proved many years ago using modular arguments. But the first time that we're able to combinatorially prove this was Garvan, Kim, and Stanton, who used t-cores, so these weird partitions, to define certain crank statistics and then give a proof combinatorially. Okay, so you say, Josh, that's great. We can define all this stuff, but do they exist? Okay, well first, let's let CTN be the number of t-cores of n, and then we stick an s in front if it's self-conjugate. So the main thing we concentrate is SC7. We'll also need these Hurwitz class numbers. So if d is a discriminant, we let h of mod d, so for us this will always be positive, be the d Hurwitz class number. What does this do? As everyone knows, this just counts the number of SL2 equivalence classes of binary quadratic forms, weighted by some automorphism group. Okay, so what was being known? So do they exist? Yes. So Ono and Granville-Ono showed positivity of CT of n for every t greater or equal to 4. So whenever you take t greater than 4, every integer has a t-core partition. There are similar positivity results for SCT for most t. So t is 8 or t is greater or equal to 10 Okay, I said we concentrate on SC7, but there were not too many that are zero, SC7 of n. So most of the time, there are self-conjugate T-cores. Okay, how many? Well, exact formula are known for T equals 2 and 3 for CT, and SCT for some small t, so here I think 2, 3, 5, and possibly 6. Okay, what else do we know? We know asymptotics via the circle method for both CT and SCT. So this is by a paper of Anderson and a paper of Albuquerque. So we know vaguely how these things grow. And you'll see here I mentioned T equals 2 and 3. Well, C4 is somehow special. And so this is O-Node C in 1997. And they showed that if 8n plus 5 is square free, then the number of 4-core partitions is given by a class number. So this is somehow a strange connection between 4-core partitions and class numbers on the right-hand side. And how do they show this? Well, they showed this in two ways. One was using generating functions and modular forms, and the other one was using combinatorial structures. And these two ideas we borrowed heavily from in our paper. Okay, what came next? Next was Ono-Raji. So this is very recent, I think last year even. So then we need a bit more notation. So we need some number d sub n, which just depends on n congruent to 1 or 3 mod 4. And you'll see here, well, this is basically comes directly from Gauss's class number formula. It's just a factor of 4 that's different. What did they show? They show that if n is not 5 mod 7 and is positive and odd, then the self-conjugate 7 cores are also class numbers, depending on n mod 4 or 8. Okay, but this is a strange restriction somehow, that n is not allowed to be 5 mod 7, so that's quite a chunk of n that we don't know anything about. And a bigger chunk is that these have to be odd. Okay, how did they prove this? They only proved this using the modular generating function type arguments. So there's a bit of a gap left. So this is something Ken noticed, Ken Ono, and pointed out to me that if we combine these results of Ono-C and Ono-Raji, we find that for 8n plus 1, not congruent to 5 mod 7, and 56n plus 21 square free, we have some curious identity. So on the left-hand side, we have 2 times the number of self-conjugate 7 cores on some arithmetic progression is the number of 4 cores on a different arithmetic progression. Why should this be true? So this was my major motivation for studying these problems. Okay, so what did we show? Like I said, we had 2 main aims. So first, extend Ono-Raji to all n. So it doesn't have to be positive or odd. It doesn't have to be not 5 mod 7. And also, I want to provide some explanation for this curious identity. So on the one hand, the first one, Ono-C, was proved with combinatorial structures, and there's a lot of structure behind that. Ono-Raji, like I said, was only proved on generating functions and modular forms. So we want some more explanation for this identity. Okay, so I guess I'll go over the results and not too much into their proofs. So what's the first theorem? First theorem is for any n, the number of self-conjugate 7 cores is some linear combination of class numbers. And here, if a fraction is not an n, we just define it to be 0 for ease. Okay, well, this is nice. There is some linear combination of class numbers, but it would look much nicer to have it as a single class number, to not have to work out 4 class numbers in this case. So for that, we need a little bit more notation. Okay, so this looks horrible. So let L in N0 be chose maximally such that this congruence holds. But the idea is we define Dn in a similar way to Ono-Raji, depending on n mod 4. And if n is 2 mod 4, this L allows us to get back in one of the previous cases. So we can just reduce if n is 2 mod 4. And the same thing, another number, nu n, is our factor in front. So it's either a quarter or a half. And again, if n is 2 mod 4, we get to reduce back. Okay, so in terms of a single class number, we let HP count the number of P primitive classes of integral binary quadratic forms. So what does that mean? Here P is some prime, means that prime p does not divide all of the coefficients of our quadratic form. So if q is ABC, some quadratic form, then p does not divide their GCD. And it comes with the same weighting as a normal class number. Then, for every n, we have this, I think, quite beautiful formula. The number of self-conjugate 7 cores is just up to some factor, the number of 7 primitive binary quadratic forms of some discriminant, depending on n. Okay, so this extends Ono-Raji, but all of the proofs here were also on generating functions using modular forms. So we also want to give some combinatorial explanation. So for this, we take a prime p, chop up our discriminant, do a fundamental and some square. And then our fundamentals, we say that this binary quadratic form, ABC, of our discriminant D is totally imprimitive if the power of P dividing this GCD is maximal. So this just means, for example, maybe here I have a 4, and a 4. This is not too totally imprimitive. Okay, so what do? We construct some map that takes self-conjugate 7 core and spits out some binary quadratic form. So for any self-conjugate 7 core that you give me, I will give you its corresponding binary quadratic form that lies in some class group. How do we construct these? These are constructed via Abaci and extended T residue diagrams. Whatever these things are, these are basically more combinatorial ways to represent various partitions. So what's the main point here is for any n, the image of this map spits out a unique non-principal genus of certain binary quadratic forms, in this case, the 7 primitive to totally imprimitive. You just think about these as some quadratic forms with a particular discriminant. Even better, suppose that L is chosen maximally, such that this same congruence hold, and some number, so here 7n plus 14 over 2 to the 2l, has R distinct prime divisors. Then each equivalence class in this genus is the image of a certain number of self-conjugate 7 cores. So this map is really explicit. It tells you, if you give me some of your favorite self-conjugate 7 cores, I can tell you the genus that it spits out, and I can tell you how many things are in the orbit that map to the same genus here, and the same equivalence class in the genus, sorry. Okay, so here I've been talking about SC7, SC4, and I guess I have 10-ish minutes left to go over some other things. Okay, so we also gave some descriptions of whether identities like this curious equality, can hold for other t. So here we only had 7 and a 4 here. So what happens if I replace this 4 with a 2 or a 3? Okay, for t equals 2, 3, and 5, there are no arithmetic progressions where ct and sc 2t minus 1 are integer multiples of one another. And here, non-trivially just means that sometimes they're always 0. Okay, even better, they can't hold even asymptotically. So even if I look at just their asymptotics, whether they settle down into something like this equation, this never happens. Okay, so what happens if I take t greater than 5? Well, for this, we rely on these asymptotics that I mentioned by Anderson and Alpogé for ct and sc2t minus 1. Here's our conjecture. There are no arithmetic progressions on which ct is an integer multiple of sc2t minus 1, even asymptotically, for basically all t. So we believe that t equals 4 is the only case this happens, a very special case. So what are some easy results towards this? Well, first of all, why 2t minus 1 and t? This is very clear if you just look at their asymptotics. We also provide some easy results on the kind of shapes of these arithmetic progressions that they could be. But the difficulty is that, like I said here, Anderson and Alpogé use the circle method. And if anyone here is familiar with it, the main terms in the circle method are not so easy to control. Yeah. So we have to look at the fraction of two main terms of circle method arguments And these things, we're not sure if they settle down eventually asymptotically. So if anyone here has worked on circle method kind of things and fractions of main terms, I'd be very interested to hear how you would deal with this. Okay, so maybe I'll end briefly with just some open questions that I would like to understand more and maybe people here could tell me about. So the results in this paper, they extend the framework for understanding the combinatorics of more general self-conjugate partitions. So our paper basically gives a complete description of self-conjugate 7-core partitions. And the same thing can be done, the same process for any T. So I can always do the same process we do in this paper and come up with a complete description of self-conjugate partitions. So what are the consequences of this? This is something I haven't had a chance to think about too much, but are there consequences in representation theory, for example? Okay, another question is that in these influential papers of Garvan, Kierman, and Stanton, in particular one of Garvan and Stanton, they give a table of groups, so certain dihedral and cyclic groups that act on T-core partitions. So can we use the combinatorial structure of the partitions that we give to explain these groups? This is something that Stanton brought up again a couple of weeks ago in a seminar. So can we use these explicit descriptions of partitions to explain these dihedral groups that act? A third question is, okay, so we know we have asymptotics of the number of T-core partitions, but we could also study divisibility. So this is a bit more refined knowledge of, say, the number of certain representations. So we want to look at the divisibility of T-cores along arithmetic progressions. And I've started briefly with Zach Tripp to look at this question. A characterization of potential progressions for T equals 4 in terms of Hurwitz's class numbers was obtained by Beckwith, Rao, and Richter very recently. I think there's a preprint earlier this year. And a final question is also one I'm looking with Zach at, is can we construct a combinatorial map between two different genera? So where does this come from? So in our paper, we construct some non-principal genus in the class group. But in the original paper of Ono-Tse in 1997, their map maps to the principal genus. So somehow we're mapping to two different parts of this class group using each of our maps from 4 cores and self-conjugate 7 cores. So there must be a way to map between genera in the class group just using our self-conjugate and 4-core partitions. So if we just look at the combinatorial structure of these partitions, can we easily construct some map between genera in a class group? And I guess I'm out of time, but hopefully this gives you all a quick overview of the main results of the paper, and maybe some people want to read it. Thanks.
Okay, thank you very much for a beautiful talk. Any questions? So I have a question. So you mentioned that there's basically a relationship between class numbers and counts of these T-cores.
Yes.
So I'm curious, like for example, there was this result of Watkins classifying, all discriminants for which the ordinary class number is at most 100. He was able to give a complete list unconditionally. Can this be used to prove any sort of results of this flavor?
Yeah, I believe it should be possible. I haven't thought explicitly about this problem. But yeah, I imagine, so a lot of information is known about these 4-core partitions, especially on the modular side, and that they're all modular forms of weight 3/2 in explicit spaces, things like this. The issue is, as you see on this slide, we're kind of forced into certain arithmetic progressions on the class number side. So we can't really escape like a factor of 4 or something in here. So we could certainly say a lot of results on Herbert's class numbers in some certain arithmetic progressions, but to get outside of that, there's not too much we can do with these T-core partitions. Maybe there are other partitions that are slight deformations of T-cores that give some closely related things, but I'm not sure they've been defined yet.
Okay. Other questions?
Mm-hmm.
Okay. If nothing, thank you very much. Let's give our speaker a virtual round of applause.